Hello, my name is Fernando Ireta. I am a researcher engineer at INRE Sophia Antipolis in France. I would like to introduce to you our results of our Wearable SLAM system, which helps to perform real-time indoor GPS tracking for emergency response agents. The system that I will present here has been tested under the conditions of the MALIN challenge, which aims to perform agent-based localization in highly dynamic scenarios. The presentation will contain these 4 titles. I will describe the objective of the challenge in the introduction, followed by a short description of our wearable system and the proposed laser visual inertial GPS fusion strategy. The 3D reconstruction process will be described here as well. I will present our preliminary results, and finally I will show our conclusion for this paper and introduce some future works. Similar to the scenarios used in the competition, we have used the following sequence that contains several transitions indoor-outdoor. The agent tracking system is initialized out of the building. The agent gets in and gets out of the building, and the system tries to maintain consistent GPS coordinates that are sent via radio to a ground station. In the left image, we can see a common tracking problem while using GPS in an indoor environment. The tracked GPS coordinates are marked in green, where we can clearly observe the degraded performance of tracking while using GPS only. In this paper, we have proposed a SLAM system that can be carried by the agent in order to maintain valid GPS coordinates, even under highly dynamic scenarios such as smoked rooms, repetitive patterns, dark environments, building floor transitions, and so on. The results that we obtain after performing sensor fusion are shown in the left image. One of the most common problems for accurate localization using different sensors is that the performance of different technologies varies according to the environment conditions. As an example, here we can observe a classic RGBD SLAM problem. The ground truth trajectory is shown in black. In case of the depth camera, when there is not enough geometric features, such as corridors or walls, the tracking methods can reach the local minima problem and can lose tracking. On the other hand, when the texture is rich, image-based SLAM methods are more robust, but the scale must be adjusted while using only one camera, and it is sensitive to lighting conditions. For dealing with this problem, sensor fusion strategies have been used for obtaining the main advantages of each sensor, with the aim to deal with the lack of robustness of each while performing tracking. In this paper, a wearable SLAM system for indoor-outdoor localization with or without GPS signal available is proposed. The main sensors are placed on the shoulders of the agent by using a tactical waistcoat. A laser camera inertial GPS fusion is proposed. The fusion is mainly based on the communication of 2 independent SLAM systems, LiDAR inertial SLAM and visual inertial SLAM. The post-optimization events generated at each SLAM are communicated and updated. 3D reconstruction at 3 different levels of details has been performed by using the consistent global 3D point clouds of visited scenarios. The proposed system has been tested under the conditions of the MALIN challenge by our team LOCA3D. Here we can observe some scenarios that were tested during the competition. The agent performs a continuous real-time tracking for about 30 minutes. We could observe the improvement of performance SLAM using LVI. However, some of the scenarios are still very challenging for our system, and keeping a continuous tracking is complicated. We have evaluated the performance of each sensor on each scenario for improving the localization. For performing tracking, we propose a sensor fusion based on the communication of the relocalization events between a LiDAR inertial SLAM and a visual inertial SLAM. The loosely coupled fusion evaluates the poses obtained by each SLAM, and it transforms them to the UTM coordinates. The generated globally consistent point cloud is reconstructed offline at 3 different levels of details. Both SLAM methods, visual inertial and LiDAR inertial, share a similar pose estimation method. After acquiring 2 sets of measurements, a feature extraction is performed on both sets. Their correspondence are found in the matching stage, and one of the sets is warped iteratively till convergence of the nonlinear error function shown here. In this equation, the variable m can represent either 3D points or intensities, depending on the geometric base or image base SLAM. For the LiDAR SLAM, a variant of the LOAM algorithm has been used. Planar and edges points are extracted from the point cloud and minimized using the Levenberg-Marquardt ICP algorithm. The pose is refined using a global optimization step using the point-to-model ICP. In the case of visual SLAM, orb features are extracted from the images and tracked using the orb SLAM algorithm. The method is enhanced with a log closure detection. For both SLAM methods, the integration of an inertial sensor is employed for prediction of the poses. Finally, the poses obtained by each sensor are fused with the GPS using a Kalman filter for the GPS UTM coordinates prediction when the GPS is not available. The video shows the performance of the wearable SLAM system in the scenario shown in the introduction. We can observe how the tracking can be maintained in the transitions indoor-outdoor. We had a tracking loss event that was reinitialized using the predictions of the inertial sensor. 2 loop closure events were detected by the visual inertial SLAM and 1 global optimization event by the LiDAR inertial SLAM. These events are communicated between the SLAM methods and we could correct the pose. The predictions of the LVI-GPS fusion are shown in the image on the left, where we have evaluated the accuracy of the system by extracting 28 GPS landmarks from an online floor plan database. The ground truth is shown in black, and the conversion of the registered floor plan by our system to the UTM coordinates is shown in blue. When the GPS is lost or the GPS coordinates are not valid, the LVI fusion tries to compensate the tracking by using the poses estimated by the wearable SLAM system. This is performed by the Kalman filter in the fusion scheme. Finally, we have performed an offline 3D reconstruction process at 3 different levels of detail. We use the planar and edge points obtained by the LiDAR plus the estimated poses of the wearable SLAM system. We reject outliers using the Seagal library. A classification algorithm is employed for detecting vegetation, floors, and permanent structures in case of outdoors, and floor, ceiling, and walls in case of indoors. In case of visiting different buildings in the recon mission, we isolate the point cloud of each building and we perform the reconstruction process for each. In this paper, we present the reconstruction of the building shown in red. After the classification, we extract only permanent structures and we detect the main planes of the point cloud. Detected planes that belong to walls are projected onto the main plane using PCA for obtaining the first level of detail or floor plan. For the second level of detail, we have employed the kinetic algorithm. The algorithm optimizes the intersections of detected planes and it can obtain a 3D model. Finally, we perform reconstruction Poisson using the Seagal library for the third level of detail. Same process is employed for outdoor scenarios. However, the third level of detail is performed only when indoor information is available. We have created a viewer that allows the user manipulate and navigate on the generated map, where the 3 levels of details can be displayed simultaneously. In this video, we can observe the process of the 3D LOD reconstruction. We set the training datasets. We isolate permanent structures. We select candidate faces of the building, and we project walls to the main floor. For the LOD1, we optimize over the intersection of planes using the kinetic algorithm. For the indoor scenario, we perform the reconstruction Poisson, and here there is a comparison of the 3D LOD1 with respect to the 3D model in Google Earth, where we can notice the precision of the reconstruction. As a conclusion, we have presented a wearable SLAM system that performs laser, camera, inertial, and GPS fusion for real-time localization, as well as a 3D reconstruction process. We have tested our system under the conditions of the MALIN challenge. As a future work, we are exploring other visual inertial strategies, such as beams fusion. We have added an illuminator and a stereo pair camera, and we are currently evaluating their performance. We have implemented a normal estimation for the LiDAR point cloud. This will help for both the localization process and the 3D reconstruction. Thank you for your attention.